So on our opposing ramps, we would have two position functions. One would start at, let's say, 60 centimeters, position x equals 60 centimeters, and would decrease with an increasing steepness to the final time, which we'll call T1F. The other would start at 0 and end up at the maximum position, which we call, well, same as the final position of this one, but in a longer time. Okay, so our ramps were set up so that the first ramp, actually well, it depends which ramp you call the first. One ramp was steeper than the other. In this case, since we get to the end of this ramp more quickly than we get to the end of this ramp would be the steeper. So we would have a graph that looks like this anyhow. Okay, now let's suppose that we get to the end of a 60 centimeter ramp that's oriented in the positive direction, where the ball rolls in the positive direction. Let's say it goes 60 centimeters in 10 seconds, again starting from rest. So let's find our velocity versus time graph. Okay, so the velocity versus time graph will be characterized by, well, it takes 10 seconds. And 60 centimeters in 10 seconds is an average velocity of 6 centimeters per second. So here's a graph where you have the average velocity at the midpoint of the segment and the halfway time here. Now the ending time is 10 seconds, so ending time, which I call T sub F1, here would be 10 seconds, but the midpoint would be 5 seconds. So that this point would have coordinates, 5 seconds, 6 centimeters per second. Now by the similarity of this triangle with the triangle I haven't drawn, but one that you could draw from here to here, this point would then have to be 10 seconds, 12 centimeters per second, because this triangle is similar to this one. So the slope of our first graph is this, 1.2 centimeters per second per second. How do I get that? Rise divided by run. I could take my 6 centimeter rise, divide by my 5 second run, and I would get 1.2 centimeters per second per second. Or I could take this triangle with a 10 second run and a 12 centimeter per second rise and divide that and get the same result. Then the 4 centimeter, on the second ramp we assume we go 60 centimeters in 15 seconds, except the 60 centimeters is in the opposite direction, so I'm going to put a negative on that. That's a negative 60 centimeters in 15 seconds, so that our average velocity is going to be what? Negative 60 centimeters divided by 15 seconds is negative 4 centimeters per second. That occurs at the midpoint. At the final point, you're going to have a negative 8 centimeter per second at a time of 15 seconds. And then from that we determine the slope is negative 8/15 centimeter per second squared. Now we talk a little bit about speeds here. The magnitude of VF1, magnitude of VF2, where VF1 means the velocity at this time. So this velocity here would be VF1, this velocity here would be VF2. And VF1 is the absolute value, 12 centimeters, well, is 12 centimeters per second. VF2 is negative 8 centimeters per second. Absolute value of VF1 is 12 centimeters per second. Absolute value of VF2, and this is the speed. The absolute value of the velocity is the speed. That would be just 8 centimeters per second. Velocity tells us in what direction we're moving, so this negative tells us that we're moving in the negative direction. The absolute value is just the speed. Okay, so we can conclude that the final speed 1 is greater than final speed 2. Okay, now what we want to do is we want to go ahead and get our velocity and position functions. And we'll pick that up in the next video.